Picking up where we left off, we talked about the base units we use in physics. We use the SI system. We do need to convert from other systems on occasion, and that's where we ended up at the end of last class was just a bunch of conversions and dealing with prefixes, which is hopefully not a lot of new things, but if there are some new ones in there, hopefully, what we did made sense. You just need to come up with some conversion factors to sort of translate from one unit system to another. And you just make sure that the units work out algebra-wise. So you can treat them like algebraic quantities. And to get from one unit to another, you make sure the old unit cancels out and then the new unit multiplies in the proper way. By that, I mean, like this example, we wanted miles on top because we're ending up in miles per hour and hours on bottom. So we want to make sure that's how they show up in our conversion factors. As for the other units that we didn't want, we need to make sure that they cancel out as we go through this conversion process. We're going to talk about the dreaded significant figures with the statement that I don't really care too much about significant figures in this class. So on exams, they're not counted, and on Wiley assignments, they are not counted. But it's worth just doing a quick recap of sig figs just to say how they work. And sometimes if you see, like in the textbook, how they're deciding to round, they are using significant figures. So these are the rules. So here are our basic rules for significant figures. The rules are non-zero digits are always significant. Say I have the number 91. How many sig figs does that have?
Two.
Two sig figs. 123.45. How many does that have?
5.
Yep. Leading zeros are not significant. So zeros in front. And that is because if you have a bunch of leading zeros, that's not really telling you anything special about your measurement. It's just telling you you probably should have used a prefix to talk about it. So in this case, if this was 0.0034 meters, you might have wanted to call that 3.4 millimeters. And so the zeros aren't adding any specificity to your measurement. So how many sig figs does this have?
2.
Two. Yep. Zeros between are significant because they actually say something about the measurement. All right, so how many does that have?
8.
Yep, so all the zeros are in between other numbers. Trailing zeros, so zeros coming after other numbers, may or may not be. So if you've got a decimal point, they usually are because you've chosen to write additional zeros to say, I know that my measurement is not just 1.2 meters to within a few centimeters or something. I know that it is exactly 1.2 meters, 0 millimeters on top of that. So how many does that have?
Is it 4?
Has 4. Okay, a couple more. How many does this one have?
3.
Yes. So which ones are significant, which ones are not?
The significant is like after the 9, so the 9, 8, and 0.
Yeah. So the 0 at the end is a trailing 0. It says something about our measurement. The first two zeros do not. They just say we should have just moved the decimal and gone with centimeters in this case. So 3 and one more.
Is it 6?
3.
It's 6. So those are all trailing zeros. I think it's just the number of zeros that starts to become alarming and you start to worry, that seems like a lot to be significant, but they are in that case. That means you know your measurement very well to be able to specify those extra zeros. But if you don't have a decimal place, it becomes a little bit less clear because it could be that that was just the easiest way to state your measurement and you really don't know it any better. So, for instance, the number 3,000, if I said something's 3,000 meters away, I may not actually know that it is exactly 3,000 meters, I may only know the first decimal of that. I may only know the first two places of it. I may only know the first three. I could know that truly it is exactly 3,000 meters. So it doesn't give me the same confidence that a decimal place does, that I'm actually choosing to report extra information that I know. So it really could have anywhere from 1 to 4. So usually it's not the best way to write things like that. That's when you use scientific notation to add that specificity, because with scientific notation, you can choose to add things after the decimal place. So writing it like this, it's going to depend on the context. So usually like what your other measurements are looking like. But if you wanted that specificity, you could say, all right, if it's 1 sig fig, 3 times 10 to the 4. If it's 2, 3.0 times 10 to the 4. If it's 3, 3.00 times 10 to the 4, and so on and so forth. So scientific notation is usually the way to go on ones like that if you want to be sure of the number of sig figs. And then the last one is how we combine measurements. So if you have a couple different measurements, you're doing some sort of multiplication or other operations on them, then the least significant thing is what determines the significance of the result of that operation. That's just saying you're only as good as your worst measurement. So let's say we have a number A equal to 2.06 and B equal to 5.6. Then if we take a number C that is equal to 2 times A times B, so multiply all of those things out, 23.072. But how should I actually report that number?
It'd just be a 23.
Yeah. 23. And how did you decide that?
Because B only has 2 sig figs.
Yep. A has 3. How did you decide about this 2 up front? Why didn't you call that 1 sig fig?
That one I don't know.
Okay, good. So this one is another one where it could be a little ambiguous, but since we wrote it as this sort of equation where everything that is a measurement is a variable, this 2 is treated as like a mathematical constant. It's like pi. It's something you multiply by because it makes the math work out. It's nothing to do with any specific measurement of something. And so constants like that, you say basically they have infinite significance. In other words, they don't factor into your consideration of significance. Have infinite sig figs in the sense that I know this is exactly 2. There is no ambiguity in that number. So although this is calculus-based physics, and I'll say a couple things about calculus, trigonometry is actually probably the most important tool in physics. And so it's got to be really, really comfortable. But the nice thing is you don't have to remember almost anything about trig other than like 5 things. So the things you do need to know are sine, cosine, tangent, Pythagorean theorem, and inverse trig functions. We know that if we've got a triangle with an angle theta, then if you have to go across from theta, that's your opposite side. If you have a side that's touching theta, that's your adjacent side, unless it is the hypotenuse, which is also touching it, but it's the long side. Sine theta is that opposite side over the hypotenuse. It's the ratio of those. And so you might remember the mnemonic SOHCAHTOA. This is the SO part of it. Cosine is adjacent over hypotenuse. Ca. And tangent theta is opposite over adjacent. So that's the TOA part. Okay, what are the units of sine, cosine, and tangent?
They be degrees.
It's a good guess. Theta is measured in degrees. Sine theta is not. The answer is actually they have no units. They are just numbers. And the reason is since they're ratios of two things, if this is measured in meters, sometimes we use brackets to talk about the unit or dimension of something. Then you've got meters divided by meters. And so meters cancel, leaving you no units. Since each is a ratio of two lengths, you end up with no units at all. Okay, you use these to find a side when you know an angle and you know another side. If you know two sides and you want the third, it's easier to just use Pythagorean theorem, and that's just a squared plus b squared equals c squared, but with our variables we've used here, opposite squared plus adjacent squared equals hypotenuse squared. Take a minute to try this one. Hopefully it is not too bad. I'm gonna just go through this and see what information I pick out as I read. You see the gateway arch, which rises to a height of 192 meters. So this height right here. I like to, if I'm not given a variable name, come up with variable names, because as much as it may not seem like it, doing things in terms of variables rather than numbers usually works out easier as far as algebra. If you have numbers, it's hard to tell if you've made an algebra mistake because you've divided the two away and you can't see what you did. If you have variables, you have not gotten rid of anything as you've gone along, and so it's easier to keep track. Your line of sight with the top of the arch is about 2 degrees above the horizontal, so I would call that theta. And that's saying, okay, you're driving in, you're looking up at the top of the arch compared with the horizontal direction. Switch to red for that. You have to look up about 2 degrees. And so we want to know how far you are from the base, which I'll call the distance d. So which trig function is going to be best to find this answer?
Cosine.
Let's start with the cosine. So if you said cosine, what are your two sides you're trying to combine?
The hypotenuse and the adjacent side.
Yeah, so do you have your hypotenuse at this point?
Yes.
You have this side length?
Oh,
So
no.
So no, you could put this in terms of cosine by rewriting d in terms of the hypotenuse length and then solving for the hypotenuse, then finding d. But it is a little bit more direct if we look at our opposite side, h, and our adjacent side, d, and that would be using tangent. If I set that up, I say tangent of theta is going to be h over d, opposite over adjacent. If I want to solve for d, I just do some multiplying, dividing. It's h over tangent theta, or 192 over tangent of 2 degrees. These point zeros up above are just relics of when I did care about sig figs. So if we did concern ourselves with it, we'd get that this is to two significant figures, 5,500 meters, or how many kilometers is that?
5.5 kilometers.
Yep. So you could do that as a conversion by saying, all right, we need to multiply meters by something to get 2 kilometers. We need to get rid of meters, so it should go in the bottom. There's 1,000 meters in 1 kilometer, and that would get you to 5.5 kilometers. Okay, so hopefully not too terrible. You don't need to know cosecant, cotangent, and secant ever, so don't worry about those. Just sine, cosine, and tangent. But those are very, very, very important. Inverse trig is just saying, okay, I have my side lengths. I want to know my angle. All right, so this one we'll just go through together. A highway will be built between two towns, one of which lies 35 kilometers south and 72 kilometers west of the other. So at that point, I would probably start drawing. I have a town A, and a town B. Town B is 35 kilometers south and 72 kilometers west of town A. We want to know the shortest highway that can be built between the two towns and what angle this highway would make with respect to due west. I also like to add kind of a compass here to help me keep track of directions. North, south, east, and this direction over here would be west. Okay, so first, the question of the shortest highway between the two towns. How could I find that?
Pythagorean theorem.
Yeah. So I've got two sides. I want the shortest highway is going to be a straight line between the two. Call that D. Then that's the hypotenuse. So distance squared equals 35 kilometers squared plus 72 kilometers squared. If I take a square root of that, comes out to about 80 kilometers. Now I need to find the angle this highway makes with respect to due west. So that would be this angle right here, theta. Someone go ahead and find that angle for me.
Wouldn't it be inverse tangent of 72 over 35?
Very close. Which is your opposite side? Which is your adjacent side?
35. It's 35 over 72.
Yep, there you go. So this will be about 26 degrees, but I'm not done. 26 degrees could mean a lot of things depending on who you're talking to, because they may think you mean 26 degrees relative to the east axis. The positive x direction is how we'll look at that a little bit later. You could mean relative to some vertical axis. You could mean a lot of things. So we add the qualifier south of west. You have to go 26 degrees below west, meaning south of it. I could also find it with my other two since I know my third side now. I know it's 80 kilometers. I could do inverse sine of opposite over hypotenuse. So 35 over 80. I could have also done inverse cosine of adjacent over hypotenuse. Those will all give me the same answer. Why would inverse tangent maybe be the best option?
Because they already gave you those numbers, so it won't be like a rounding error or something.
Perfect, exactly. So the less we depend on our own calculations, the better. So another thing worth pointing out here is that bit about direction. So that's south of west, just to emphasize. Say I'm asking you 4 directions from town A to town B. If you just tell me, just drive 80 kilometers, I'm going to wait and see if you tell me a little bit more, because that's just not enough information to know which way to go. There's also places that are 80 kilometers from A, but only B is 80 kilometers away and 26 degrees south of west. That is enough information to fully specify which way you need to go. If I didn't know that information, I just knew 80 kilometers, you would be telling me actually go anywhere on this circle and hope for the best. I'm going to add a blurb here. So I'm going to add a page for it about calculus. And it's not going to be anything that helps you calculate anything. It's just going to be how we view calculus in physics. And some of this gets a little bit hand wavy. A math class, it would not fly. Start with derivatives. Geometrically, it's the slope of a function at a point. If I've got some curve, and I say, for whatever reason, I don't have any physical reasons at this point, but I've got a function f of x. I want to know what its slope is right here. That's what the derivative tells me. df dx evaluated at x. So this point right here. But kind of conceptually, it tells you how much quantity f, whatever it is, changes when you make a small change in quantity x. Probably better to say per small change because it's almost like a ratio. But it's just saying, okay, say f is position. It's how much your position changes relative to, if x is time, a small change in time. And so that gives you information about speed, how fast something is moving. So derivatives are really important because they tell us the rates of change of things relative to each other. How I actually find it is I consider a point a little bit farther away, x plus h, where that distance is h. This is going to be f evaluated at x, and then up here, f evaluated at x plus h. And so the slope of the line connecting those 2 points is rise over 1. So the rise is f of x plus h minus f of x. That's how high up you go. And then the run, x plus h minus x, that right there. And so if I want to know at a single point, I just consider closer and closer and closer points to the one I'm interested in. And so I'll do that in red. I just consider now the slope between those 2 points, and then those. And then eventually I get to this limiting case of my 2 points are overlapping. That's my derivative. And that's where we add in the limit as h goes to 0 bit. It's just saying make your 2 points you're finding the slope between closer and closer and closer together. So df dx is just how much f changes per tiny change in x. Integrals, geometrically, it's the area under a curve. So if I've got my same function f, I want to know the area under the curve between a and b. Let's start with my interpretation of that. So just the sum of many small pieces of something. So integral a to b f dx. This means sum from a to b of small bits of f. The goal of integrating something is finding its change overall over some span of time or some span of distance or whatever else. So we're adding up the small changes to get the overall large change. That's the benefit of integration in physics. Or if you want to find the total charge in something, you can find how much is concentrated in a certain area, a tiny bit of that charge, and then you add up all of those little bits to get the total charge. We'll do that in physics too. You know how to find it. You just break your area up into tiny little rectangles. So I'll do that in a different color of width delta x, and you're just adding up those areas. So the width is delta x, the height is f of x, with a little bit of round off error if you don't take a limit. And if you keep adding up those little rectangles and consider a limiting case of very tiny rectangles, so this is pretty informal here, but limit delta x goes to 0, sum of f of x. We had an index to say we move from one rectangle to the next, delta xi. That gets you your integral of f dx. Okay, so that's the Riemann sum thing, but just visually, you can see if we add up a bunch of tiny rectangles, we approximate the area under the curve. If we consider tinier and tinier rectangles, we get the actual area under the curve. And last thing, the relationship between the two, the fundamental theorem of calculus, it just says the sum of many small increments gives the total change in something, the total change in a quantity. That's the sum of many small increments. And that's equal to f of b minus f of a, which is the total change between a and b. That's our main pieces of calculus. Oh, and finding the maximum of something, which is just, if I want to know the maximum, I look at where the slope is 0, so where the derivative 0, because that's putting me at the top of my hill. When you're standing at the top of the hill, it's flat up there. So the derivative is 0, and that lets you find where that happens, where you have a maximum. All right, then I'm going to jump over to the chapter 2 notes, and we will start discussing some physics. So motion is the main focus of physics 1. Study of motion is called mechanics. We're going to start by looking at the properties of motion, just what features it has. That's kinematics. And then later on, we're going to look at what causes that motion or changes it. So something's not moving, now it is. Something did that. If something was moving a certain way, but then it turned or it sped up or slowed down, something caused that. That's dynamics. Okay, so start with the simplest possible case and build up from there. And you will find in every chapter, the chapter starts with the most obvious kind of brain-rotting statements you could think of. But by the end, you're left thinking, what happened? How did we get here? And that's sort of physics, is just taking a simple idea and building on it until it becomes almost unintelligible, but it tells you something more than what you started with. Okay, so kinematics of particles moving along straight lines. So a particle, you might think of a little concentrated point, and that is what it is, but we can treat anything, any object that moves without rotating or stretching as a particle. So a car is more or less a particle if you ignore the fact that the tires are rotating. We can be treated as a particle if we're not too concerned about what our individual limbs are doing, if we're just concerned about our effective motion. Really, we'll get to this later, but we're talking about the motion of our center of mass. And so anything can kind of be treated as a particle if you're only worried about how its center of mass is moving. Anything more complicated than that, you need to start considering things like what's called rigid body motion or even soft body motion, and that gets deeper in the weeds of the math as well. So we don't want to worry about all of that right now. Okay, so the first thing we need to consider is something's position, where it is. Object's location relative to some reference point. So we have to choose a reference point because otherwise we don't know what we're saying, like where we are in the first place. Usually we kind of do that intuitively, but in physics you have to explicitly choose a reference point. So this works a little better when we're in person and I'm standing in front of you. But let's just say someone's sitting right here. I want to locate them relative to my desk. So that'll be my reference point. And usually we also call that the origin of a coordinate system I want to use to measure. So once I've chosen a reference point, I create a coordinate system based around it. In this case, to locate any point in a classroom relative to my desk, I need two axes to say how far horizontally and how far vertically, or I guess farther into the class, I need to move. And so I might say, okay, it takes me to get to this person, right? I'd take the smart way of going directly there, but I can consider that as a certain number of steps horizontally and a certain number vertically. And so I'm effectively locating them at the coordinate 1, 2 in this classroom. And I would start adding my little axes, my tick marks for number of steps. I'm taking pretty big steps here if I'm just stepping from desk to desk, but that's the idea. Okay, and then you can locate any point in the classroom based on the number of horizontal and vertical steps it takes to get there. So I want to put my units here, steps and steps. All right, in 3D, right, if I'm jumping on the desks, I have a third coordinate and that just says how far vertically I am, and that's probably relative to the floor. So still nothing surprising here, nothing interesting. For 1D motion, we just need one axis. It's whether I'm going left or right, or if it's up or down, or east or west, whatever. If it only requires two directions, I can use one axis. And we tend to, because we read left to right, call right the positive direction and left the negative direction. I do wonder if some countries that read right to left do it the opposite way. I'm not sure. But this would be our origin. Okay, so to talk about motion, we need to talk about changes in position. So that's what we call a displacement, a change in position. From some initial position to some final position. Okay, so I'm in my car. I start out at position x0 relative to some reference point. Maybe it was my house, and I'm x0 away from it when I'm at the foot of the driveway. To get to work, at this point, assuming that I'm just driving down a straight road to get there, wouldn't that be nice? That puts me at position X. So my displacement is just that change in position. Delta X. Delta just means difference. It's a Greek letter, and it can mean a difference in any quantity. So we'll see it pop up a lot. It's just a change in a quantity. So if I start at position X0, what do I need to do to get to position X?
Add delta x.
Yeah. So if I go this far, delta X, I will get to X. So displacement is just final minus initial position. It is X minus X0. I'm just rearranging that first equation. So final minus initial. And that is a common trend that I do not want you to forget. Any change in a quantity, any delta, anything. We'll talk about changes in kinetic energy, changes in momentum, changes in a lot of things. It's always final minus initial, always. Do an example. Suppose you want to walk to a store 1,000 meters east of your house. We want to take your house to be the origin of a coordinate system and east the positive direction. So we're going to say this is your positive x direction, east. This is the store. And we want to know in each of these three cases what your final position is, the total distance you travel, your displacement, and the size of your displacement. We'll see what that distinction between part C and D is in a minute. In terms of this coordinate system I've set up, where this is my initial position and it's 0 meters, what is my final position in part 1?
1,000.
Yeah, and I want to be a little bit more specific because I could have gone west, right? So this is positive 1,000. I've gone 1,000 meters in the positive direction. And normally we really don't include the positive. So you're right in just saying 1,000. But here, if we do that, it's going to be a little bit easier to see a distinction between two different things. So our initial position is 0 meters. Our final position is positive 1,000 meters. How far did I travel? So I went from here to there. Call that a displacement from my house to the store. How far did I go?
1,000 meters to the positive direction.
So this, you're going to hate me. When we talk about distance, do we specify which way we went? If I'm just asking you how far did you go? So if you're running around a track, for instance, does it matter that you've rounded the track if I'm asking you how far you've run?
No.
No, you just tell me I ran 2 miles. That might be that you went around the track 8 times if it's a quarter-mile track. But what matters is your total distance you moved. And so it's just a number. It's not a which way I went. And that is a distinction between it and displacement.
So it's the difference in distance in a vector, right?
Exactly. So displacement is a vector. Distance is not. It's a scalar quantity. And we'll talk a lot more about that distinction in a bit, but that is the idea, the distinction between a scalar and a vector. Okay, what is my displacement though? Okay, final minus initial. So positive 1,000 meters minus 0 meters. That is positive 1,000 meters. So that does have a sign. It has a direction to it. If I had gone west from my house, that would be a negative 1,000 meter displacement. So the positives and negatives are relevant here because it bakes in the idea of direction. But part D, the size of my displacement is just that 1,000 bit. So a lot of times we write it, the magnitude as an absolute value. That is just 1,000 meters. That's the size of my displacement without any concern for direction. So at this point, you're probably thinking distance and the magnitude of displacement are the same thing. They're not always. So just keep that in the back of your mind. Okay. Help me with part B. You walk from the store back to your house. So this is your displacement now. You go right to left. Call that your displacement from the store to your house. What is your initial position?
Is it 1,000 meters?
Yep. And it's 1,000 meters in the eastward direction, so positive 1,000 meters. Final position?
0.
Yep. You're back at your house. You're back at your reference point. Okay. So how far did you travel?
Is it 1,000 meters?
Yeah. Same as before. You went 1,000 meters. But what is your displacement?
1,000 meters in the east, or not east, in the west direction.
Yeah. And if we do final minus initial, so final was 0 minus positive 1,000 was our initial, we will get negative 1,000 meters. So this right here is that westward bit. So displacement is automatically baking in direction in how we calculate it. The magnitude of that displacement is still just 1,000 meters. And then talk about the round trip. You walk to the store and back home. So what's your initial position?
Your initial position is 0.
Yep. And your final position?
0 as well.
0 as well. How far did you travel?
2,000 meters.
2,000 meters. But what is your displacement?
0.
0. It's final minus initial. Okay, there's the big difference. Displacement is only worried about your overall change in position. No matter how far you went, if you went around the world but ended up back at your house, your displacement is 0. The distance could be very large. So they are two different things, and one of them cares about direction while the other does not. So distance doesn't care, displacement does. And the magnitude of your displacement is also just 0. So the sign of displacement we've seen tells you about which way you went. If it's positive, that's overall motion in the positive direction. Overall is an important word here. If I did that running back and forth, but I ended up only halfway between, so I'm at 500 meters, my displacement is only 500 meters in the positive direction, even if I went past that during the trip. Negative is overall motion in the negative direction. 0 is no overall change in position. So even if you run around the entire world, if you end up back where you started, then your displacement is 0. We also saw that the magnitude of displacement is not always the total distance traveled in that last example. So the distance was 2,000 meters, our displacement magnitude was 0. It is related to distance in a specific way. It's the shortest distance you could travel between those 2 points. So the shortest distance between where I am right now and where I am right now is 0. And last, displacements are additive. So if I called this last displacement, even though it was 0, my displacement from my house to my house, I can say, all right, my displacement from the house to the store plus from the store to the house equals the displacement from my house to my house. All right, is that really true? What did we say my displacement was from my house to the store?
1,000 meters.
In the positive direction, right? 1,000 meters east. When I went from the store to my house, what was my displacement?
1,000 meters west or negative 1,000.
Yep. Okay, I can see that adds up to 0. Was that my displacement from my house to my house? Yes. Okay, that's always true, no matter what displacements you're talking about. It's the idea that if I take 2 steps forward, then 1 step forward, I have overall taken 3 steps forward. But if I take 2 steps forward and 1 step back, I have taken overall 1 step forward. +2 plus -1 is +1. Okay, so that's a nice property of displacement, and that's going to lead us to the idea of what's called vector addition in the next chapter. the key distinction we're seeing is displacement cares about direction, distance does not. Displacement's a vector quantity, meaning it requires both magnitude, the size of that thing, and direction. Distance only cares about a number. Only magnitude matters. So, real fast, what are some other vector quantities you can think of? Some things that you do need to specify the direction in order to get a full description of it.
Velocity.
Velocity.
Force.
Yeah. Acceleration, we'll talk about in a bit. That one's maybe not as obvious. Momentum, there's several. Okay, scalar quantities. That's a little bit easier. We're more used to those in everyday life. Things that only care about a number to describe them.
Degrees.
Yeah, degrees. So angle is the quantity. Let me put that. Really anything that you just look at a number on a dial or a number on a meter or something, and that's all you need. So temperature, even though it can have positive and negative values, that's not with reference to a direction. That's just with reference to a particular reference point. Mass, how much stuff you got, time, also you could argue has a forward and a backward, but usually in physics it's treated as a scalar quantity. Okay, so that's the distinction. Direction matters for vectors. Okay, so we've seen that how far has at least two answers. You could talk about the distance traveled or your displacement. So how far you went or your overall change in position, and those can be two different things. How fast can also mean different things. In fact, it has about 4 answers at least. Start with average velocity. That is just something's displacement over the time it takes. Change in position over change in time, or final minus initial position over final minus initial time. Okay, what are the units for average velocity?
Meter per second.
Okay, we are going to first talk about it in terms of graphs because that leads us pretty naturally into what we talked about for derivatives. So we call these position time graphs because creatively we've got position on the vertical versus time on the horizontal. So we've got the position of some animal over time. We want to find the average velocity of the animal between 1 second and 4 seconds. So 1 and 4 and 1 and 4. What is in the first graph the initial position of that animal?
-2.
Yep. So initial position is -2, and it is confusing. You're really tempted to look at the horizontal axis for position, but it's the vertical axis. And so one thing that can help is if you kind of turn your head to the side. Motion is really happening along the vertical axis. So west would be downward in this picture, east would be upward. Okay, what about my final position?
Also -2.
Yeah, so pretty quickly you can tell what's happening here without worrying about calculating an average velocity. What's this animal doing?
Standing still.
Yeah, it's not doing anything. It's a very boring position time graph. But average velocity does capture that for us. It tells us the same information. And that's really the value of checking with these equations, that they tell us what we think they tell us. So final position was -2, initial position was -2, final time was 4 seconds, initial time was 1 second. And that's going to be 0 because -2 minus -2 is 0. And that's going to be true for any time interval. Okay, now we get to a little bit more of an interesting one. What is the initial position of this animal in the second graph?
-5.
So at the very beginning, yes, like when we started the clock, but like at 1 second, that'll be -4. Okay, what about the final position, meaning the position at 4 seconds?
+2.
Yep. All right, so what is, let's see, so the initial time was 1 second and the final time was 4 seconds. So what is the average velocity in this case?
3.
Okay, let's check. So my final position was +2 meters. My initial position was -4 meters. My final time was 4 seconds. My initial time was 1 second. So 2 minus -4 is 6. We divide that by 3. It's going to be +2 meters per second. In other words, 2 meters per second in the positive direction. You may notice that another way I could look at that is this is the time interval, delta t. This vertical change is my displacement, my change in position. And so my average velocity is the rise, the vertical, over the run, the time interval. So my average velocity is what on this graph?
The slope.
The slope. It's the slope of this line connecting my 2 points. That's not necessarily always sitting on the graph, but it's that slope connecting those 2 points. And that's true in the first graph as well. It's just, what is the slope of a horizontal line? It's 0. Has no slope. Okay, so average velocity is always the slope on a position time graph. Average speed is not displacement over time, it is distance over time. And so if you understand the difference between distance and displacement, you understand the difference between average velocity and average speed. We use total distance so little, at least in physics 1, that I don't have a variable for it. But it also has SI units of meters per second. Unlike average velocity, this doesn't have a direction. And so average velocity is a vector quantity, average speed is a scalar. Okay, I want you to take a couple minutes to attempt this one. Don't worry about these boxes up at the top. We'll draw something in there in a minute. I just want you to calculate the average velocity for these 3 segments it asks about. Okay, and the numbers do line up how you think they would. So at 200, it is 400, and so on and so forth. So just take a minute, try and find those average velocities for these 3 segments. So segment 1, we're talking about this part right here, somewhere along that line. So I need to find 2 points on that line that I can find the slope between. It looks like 200 and 400 line up, as do 400 and 800. And so I'm just finding this horizontal change and this vertical change. The horizontal is the change in time, the vertical is the change in position. And that should give me the slope between those 2 points, which is average velocity. So what did we get for that?
2.
Yeah. Can you be more specific?
2 meters per second.
Even more specific.
Positive 2 meters per second.
There you go. And yes, you were saying that already and implying the positive. I'm just being very pedantic about that positive because it has value now. It's not just kind of a placeholder. It is actually telling us about direction now. It is a useful thing to us. And if we leave it out, we can start to mix up scalars and vectors. And I'm going to leave it out at a certain point. I'm going to forget, but I just want to be very neurotic about it right now. So we're kind of clear on what it's telling us. So positive 2 meters per second. And I should have even put positive here and positive right there. Okay, so my slope is a positive number. What does that tell us about the overall motion of this bicyclist? Which way are they moving?
They're moving forward.
Moving, which way did we call the positive direction?
East.
East. At first, they're moving with a positive velocity. They're going one way. Who knows how a bike looks? No one's ever seen a bike, right? Who knows how a human being looks? No one's ever seen a human being. Lord. Segment 2 is pretty easy. What's his average velocity?
0.
0, right? You can read that right off the graph. Between any two times in this segment, we're not seeing any change in position. If I wanted to do the calculation, I could say he was at 1,200 meters at the end of that segment and at the beginning. And that was between 1,000 and 600 seconds, but I really don't need to realize that that's going to come out to 0 meters per second. Okay, so my slope there was 0. What's this guy doing?
Stationary.
Yeah, he's just sitting there. He's chilling. All right, now for segment 3, we'll just do it real fast. So if I just pick 2 points, maybe like 1,800 seconds, that puts him at 400 meters. That's his final position. And let's say this one right here, that's at 1,400 seconds. By the way, do you see why it doesn't really matter which 2 points I choose for each segment? Like which times and positions I'm deciding to use? By that I mean, I could have also, for this third segment, started with this point as my initial point and gone with something like right here as my final point. It doesn't matter to my calculation of average velocity for that segment because I'm going to get the same slope regardless. If your position time graph is a straight line for some amount of time, it doesn't matter what 2 points on that line you use to calculate the average velocity because you're going to get the same answer regardless. And we will pick up on Thursday. Are there any questions closing out?
Yes, I have one. Is there any more assignments due or that will be posted this week, other than the chapter 1 things that are already on Canvas?
So yeah, the chapter 1 that is due on Thursday. I think I will post the chapter 2 practice today since we started the chapter. But since chapter 2 is a normal length, chapter 1's very short, then we'll kind of get on a better track of not having too many overlapping assignments. So they will overlap right now, but you'll also have a week from today at least to do the chapter 2 one. Probably a little bit longer because it may take us just a little bit of extra time to finish out the chapter.
Alrighty, thank you.
Yep. Since you mentioned that chapter 1 thing is due Thursday night, everyone. So don't forget about that. If you're having any trouble with Wiley, please let me know. All right, everyone have a good day and stay warm as usual.